All right, so in this part, we are looking at basics of machine learning. And the first basic, you already saw a first learning algorithm or got a glimpse of it with the stochastic gradient descent LMS algorithm, least mean squares algorithm. But now we want to you look at a different basic learning algorithm for concept learning, which is for a nominal feature space. So we're looking at a completely different feature space, and we are now building from the ground up how we can learn in that feature space and what this explains us about what classification and machine learning actually is. After that, we are looking at regression and then evaluation. So, rule-based learning from simple concepts. At the beginning of every new learning paradigm that I will show you throughout the lecture, we will look at so-called problem setting, or in most cases a classification problem. So classification problems will be our running example. And usually it's binary classification that we are looking at, so classifying some object into one of two classes. But there's also other kinds of classification problems, and on some occasions we will also see them. The setting is usually the same, and the learning task is also very similar always. The setting is we have a multi-set of feature vectors. Do you still know where they come from?
What was the question?
Where do the multi-set of feature vectors come from?
Like it comes from what do you mean by what?
Yeah. What is this the result of? The multi-set of feature vectors. Yeah.
It's from our alpha function.
Yes. Correct.
And models the real data into our
Yes. Correct. It is if we used all objects in the world and applied the alpha function to them, we would get this set. Oh, sorry. It is a multiset because it could be that we chose characteristics which are similar for different objects, or the same for different objects. Therefore, some objects of the real world which are different in the real world are mapped to the same feature vector, even when they might have different classes. All right, then next we have two classes, no and yes is the set of two classes. In this case, we can have other kinds of two-class classifications where 0 and 1, -1 and 1, or these two symbols here are the outcomes, or even something more high language belongs to a concept or not. It's all the same. How you model the two classes in a computer doesn't matter. It's just the semantics that matter, and we stick with yes and no for now. And we have examples. The data that has been recorded by someone, namely examples for real-world objects which have been run through our alpha function to create our feature vector, and the classes associated with them as given us by an expert. This is a subset of the Cartesian product of the of the multiset of feature vectors with the classes. And then our task now is to use D in order to fit a decision rule Y. And how this decision rule now looks is the subject of the rest of this lecture. Starting with an example. What concept do we want to learn? We want to learn whether my friend enjoys surfing. So windsurfing. And we model the days on which he enjoys surfing with the following 6 features. How's the sky looking? What's the temperature? What's the humidity? What's the wind? What's the water conditions? And what's the weather forecast? And what we see here is a couple of examples that have been given us to my friend. Whether they enjoy surfing on that day or not. I've been asking 4 days, and we see that on 3 of the days, the sky was sunny, and on 1 it was rainy. On 3 of the days, the temperature was warm, and on 1 it was cold. on 3 of the days, the humidity was high, and on 1, it was normal. On all of the days, there was strong wind, probably a good idea for windsurfing. And the water was warm on 3 of the days, but cool on another. And on half of the days, the forecast was the weather would stay the same, or on half of the days, the weather would change. And this is then the mapping, the gamma function, that our friend gave us. From these examples here, with these conditions, with that conditions, they would enjoy surfing. And with those conditions as well. So the only difference here is the normal humidity versus high humidity. Everything else stays the same compared to the first example. On this day, when it was rainy, cold, and otherwise the same as before, there was no enjoyment of surfing. And otherwise, again, what's the difference here to the first 2 examples? With the water, if the water is cool, it's also not a problem, and if the forecast is about to change, also not. So we have some kind of subtlety here, and from these conditions here, from these nominal variables, which are just not measured in any way, so they are not in a real, they're not real numbers, but just fuzzy concepts. We still can learn. If we look at the 6 features that we have, I don't know. If we look at the 6 features that we have, we see these are the domains of the features. So we have 3 conditions for the sky, and respectively 2 conditions for the other variables that we are looking at. So how many possible different vectors can there be? How many possible different examples can you tell?
Is it 20 or like?
How many possible different examples can I create based on these values? How many possible different ones here? Yeah.
I believe 96.
Yep. Very well. You're good with math. I wouldn't be able to calculate that. Well, how can you give the calculation?
I mean, you can just multiply
Yes.
the amount of elements that are in
Yes.
each dimension.
So the size of the domains, 3 times 2 times 2 times 2 times 2 times 2 gives 96. So I can create that many examples. So if my friend had a lot of time, or if I would ask them after all of these days would have happened, and I would get an extensional definition of enjoy surfing, I could just monitor that person on as many days as necessary to see all different conditions, and then ask, did you enjoy surfing or not? And then I would have what is called an extensional definition. I would have just explored the entire space of possibilities, and then I have learned by heart what's going on. It's rote learning, or it's exhaustive enumeration of the possible definition of that concept. Extensional means we just list all possibilities that belong to the concept. Yeah?
But it's a learning anyway, right? Even the extension.
Well, you could call that learning by heart. Rote learning. Yes, it's a pathological case of learning, because no, in that case, there would not even be learning involved. It would be knowledge. You would know. You could always tell. There is no risk of making errors anymore. Yeah.
Would it also be possible that the outcome would be different, even if the features are the same, if there are other factors that...
Yeah, that is of course we were the modelers. This is the variables that we record. So if we make the wrong choice and somehow get contradictory data from the person, on one day they enjoyed it, on another they didn't. For example, personal vocation or having trouble at home or something like that, we wouldn't know. So we would just get contradictory data given these 6 variables, and something would happen. Keep that in mind. So even waiting for all these 96 days to have happened at least once while the guy was surfing and us being able to ask them whether they enjoyed it would take a long time. So that's not feasible, even for such a small example. So what we really want is an intentional definition. We want to learn what is necessary and what is sufficient for my friend to enjoy surfing. The question now is, how can we get that? Just from these 4 examples. And what we are now want to come up with is a hypothesis that is capable of capturing that concept. How can we do that? So what we can do is, let me see. Yeah, no. Let's start with this definition first before we get to an actual solution to that. Think about what hypothesis you might want to look at, or how you might want to formulate some kind of way of coming up with a definition. But first, we define what is a concept and what is a hypothesis. So we are given a set of real-world objects O and a feature space composed of our 6 features, and a model formation function that maps between the two. Based on that, we define our multiset of feature vectors that is the outcome of basically mapping everything in O to X. And this gives us the multiset of feature vectors. A concept O is a concept O is a subset of O. So on any real-world day O, my friend might enjoy surfing. So that induces a subset of days. And that means this induces a subset of days in our multiset of feature vectors, somehow. Concept learning then means now, given an example set of D, we want to learn a function that somehow maps this feature vector to 0 or 1 or yes and no or something. And it should only return 1 if that feature vector is part of the concept, part of the subset. So a concept of a nominal learning problem is a subset of the feature vectors. That's all. We want to learn a subset. Looking at this specifically again, here's the, this is basically again the recreation of the graphic that you saw before in a more specific case. We have a concrete function y, and that is called our hypothesis. And the set H of all considered hypotheses, so all different instantiations of our function, is called our hypothesis space. So we are searching in the hypothesis space H for that function which maximizes the match between that function and the real world function of my friend enjoying surfing. So what kind of hypotheses and hypothesis spaces could be built now? All of this is also written there. Let's go. I thought this was coming earlier. Let's go back here. What kind of hypotheses could we formulate? What would you say? Do you have an idea how we could formulate this problem? Yeah?
I mean, could you say that my friend only wants to go surfing if it's sunny and warm?
Yes, okay. We're picking 2. What about the other variables? Yeah, we have more variables.
Maybe we can say if the temperature is cold, my friend doesn't like to go surfing or doesn't enjoy surfing.
Yeah, it's also a possible hypothesis, yeah. But you're always looking just at one feature. You're not looking at all features. Why do we have recorded so many features if we don't use them? Yeah?
I mean, one assumption we could also make is that my friend enjoys surfing every time unless it's rainy, cold, the humidity is high, the wind is strong, the water warm, and the forecast is it will change.
Yeah, possible. What kind of formulations are you using there? What kind of formal math-like object are you formulating? It's not a linear function, obviously. Which other kind of math are we using here?
It's a matrix.
No. If this, then that. logics. You are formulating a logical formula. Huh? And now you can decide which kind of formula do you want. Do you want to make restrictions or not? We will start with this very simple kind of logical formula, just a conjunction. A conjunction of these feature values, which is supposed to then define whether something is, whether my friend is enjoying surfing or not, which is supposed to define that subset here, which is our concept. So this subset here is the same as enjoy surfing, in a way. All right. So now we are given an example set D, and it contains usually positive examples and negative examples as per our learning task. Classified as positive means that if we have a model function, like a conjunction of feature values, or a hypothesis for that, then given an example is classified as positive if the model function classifies it at 1, if and only if. So this is a very important concept here, if and only if. Have you ever heard that? It is only the case, so it goes both directions, it's an implication in both directions. If the model function if we calculate the model function, we get a 1. And if there's a 1, the model function will also, let's put it that way. So an example is classified as positive. We can only say that an example is classified as positive if the model function calculates 1. And if the model function calculates 1, we call the example classified as positive. And that is regardless of its actual class. So this has nothing to do with what the reality looks like. It is only to do something with what the model function looks like. So if and only if means it goes both ways. And we call the model function consistent with the example if and only if its outcome is the same as C. So the same as the real world example. The model function, if the example has 0 for class, then the model function is consistent if it also outputs a 0. If the example has 1 for class, the model function is consistent only if its output is also 1. So the model function is consistent with the examples if and only if its output corresponds to C. And that's, you see the difference here, right? Not to be confused. And we can extend that or generalize that. The model function is consistent with our data when it is consistent with all of its examples. So for all examples in the data set, the model function outputs the correct class C. That is what we want anyway, or what we hope for. That is all we want to learn from the data, that model function which is consistent with all the data that we have. Hoping that this model function then helps us, helps us to classify unseen examples. The whole idea of if and only if is also explained here again. It is logical equivalence in that sense. So saying that something is consistent if and only if means it is equivalent with the other formulation. It is not to be confused with implication of any sorts. That's important in this case. So now let's look at the structure of the decision rule. We already saw that we want to use logics in a way, and what we could do is use a logical conjunction of feature value matches. How can we formulate that? No, given the examples before, we saw some contradictions there. So we need to make room for some contradictory statements. Going back to the examples here, you see sometimes they enjoy surfing when it's normal humidity and sometimes when it's high humidity. So we need to allow for that somehow. The domain of that feature does not allow for any wildcard. So we need to introduce that. And this is what happens now. We are given three kinds of parameter values for our model function. It is a literal, namely exactly the name written in the domain of a feature. Could be sunny, cloudy, warm, high, strong, whatever. It is a wildcard, any of a given domain. And it could be the contradiction, or this is called perpendicular. So none of the variables in the domain.
How do we define a wildcard?
It is defined as any value from a domain of a feature, no? Regardless which one. Just like wildcards, you may have heard of regular expressions.
Yes.
Yeah, okay, just like those wildcards. Yeah. Could be anything. So what we now build is a logical formula. Never mind the I at first. We are using the first feature value. We are using the first feature value and compare it to our hypothesis parameter. So theta 1, sunny equals sunny, for example, in one example. Then, for the second feature, we look whether it's warm, and the parameter of our function might be a question mark, might be this, and we might go on with this. So this is how it concretely looks, and then we interpret the formula. We interpret whether this formula, given an example that we are actually getting, evaluates to 1 or 0. So this formula, this I function, just maps logically to 1 or 0, given whether this function, whether this conjunction of atoms is correct or not. This is just a comparison between literals and question mark, or literals and the perpendicular. So it's just a special equals. When there are strings, it's just string equals. When there's this, it gives true if any value is there. And when there's this sign, it gives false anyway. What we can do now is to create a truth table for this function in its general form. The truth table just tells us, here are the literals for our parameters, here are the literals for our features. The feature values of any given examples are always literals, because we don't have days where it's just question mark outside, right? But we want to be able to formulate hypotheses that are more general than that, or more specific than that accept any given condition on any variable, or that reject any condition on a variable. And then we can, for each of these comparisons here, say if a literal equals a literal, then it's true. So if this comparison evaluates to true, so if the two literals are the same, then the outcome of this function is also true. So we define this function this way. If the literal is unequal, so if the strings are not equal, then the function is also false. If we have a question mark and a literal, that evaluation here, this equals, the string equals, is undefined. But since this is a question mark, we say true. If we have the contradiction and a literal, then this comparison here as strings is undefined. But since this is a contradiction, we say false. Yeah.
When will the contradiction be true?
Cannot be. Never. It's always none of this. So if we say the condition, if we say in our hypotheses that at no temperature my friend enjoys surfing, then they will never enjoy surfing.
Yeah.
Mhm. So this is a really hard cut. Whenever in one of our hypotheses this sign appears, there will always be the answer of the model function 0. So this is how we then formulate the parameter vector of this function. So these are the parameters, and this is the parameter vector. Everything else is fixed by definition of our model function, model formation function, that gives us these axes and these features and how we designed our feature space. But this is the thing, these parameters, which we can vary now and look for the right setting of parameters that will allow us to learn the concept. For example, we could formulate this hypothesis. Sunny, warm, question mark, strong, question mark, question mark. If you look at the examples from before again, sunny, yeah, checks out in all three examples. Warm, checks out. And now I forget, question mark, strong, checks out. Question mark, checks out. This is a valid example. So we can say that this hypothesis is consistent with D, meaning for all examples in our examples in our small set of examples, the hypothesis evaluates to the true class. Okay? It also means that for all positive examples, the model function is positive, and for all negative, it is negative. All right. Again, everything is explained here again, just so that you can read up again. Now, we can formulate very extreme hypotheses given the two new kinds of domain values that we introduced. We can formulate the most specific hypotheses and the most general hypotheses. The most specific hypotheses will have for all parameters just the contradiction. At no condition whatsoever and no combination of conditions, my friend enjoys surfing. They just don't enjoy surfing. As opposed to the most general one, at every condition they enjoy surfing. We could formulate that just by setting wildcards everywhere. So it doesn't matter, they will always enjoy surfing. They're obsessed with surfing. All right. Yeah.
I do have a question. So wouldn't it be enough if we had just one field that is a contradiction?
Yes.
Because that one field
Yes.
will never be, okay.
Yeah, would be enough. This is just the most extreme formulation that we could choose. But in any one contradiction would be sufficient. But we will see there are relations between hypotheses which put them in some kind of order. And this will come in more or less the next slides already. So, the model functions always being 0 or always being 1 are called maximally specific and maximally general hypotheses. So this sign means equivalent to. No x is classified as positive or as negative respectively with regards to these most specific or most general hypotheses. And this gives us, as I see, some kind of an order among hypotheses that we can formulate. So we have this feature space, the feature vectors in our data, and we can now look at different relations between hypotheses. And given their construction, whenever I say something more specific, I make the model functions more make the hypotheses more specific. So somewhere at the top here is the most specific hypothesis. Somewhere at the bottom here is the most general one. Everything in between, any combination between question marks, perps, and actual literals will be somewhere here ordered somehow. And this ordering is a partial ordering, as you can see here. So it forms a directed acyclic graph. It's not a total order. I cannot say for every pair of hypotheses that one is more specific than the other. You can see this with the hypotheses H1 and H2 here. Sunny, question mark, normal, question mark, question mark, question mark, and sunny, question mark, question mark, question mark, warm, question mark. So how do I reconcile that in the third position here, there's a question mark here, but normal there, which would make this in this position H2 more general, whereas at the same time, in the penultimate position, there's warm in H2, but a question mark in H1, which would make this, according to this variable, more general. So these are on the same level. Neither is more general than the other. Whereas if I look at H4, sunny and everything question mark, this H4 is definitely more general than the two of them. because neither in the third position nor in the penultimate position there's actual literal, and in both cases it's a question mark, making it random or making it arbitrary, and the only thing that is consistent is the sunny. So I can just set this question mark to normal and I could just set this question mark to normal and would arrive at range 1 from H4, and I could just set this question mark to warm and would arrive at H2 starting at H4. So I could make this hypothesis more specific, or I could make these hypotheses more general just by switching out the literals. And this is actually what learning entails here. We will look through this space. All hypotheses that we can formulate. So now that we are at this, if I go back here, how many hypotheses can I formulate now? So we saw that just using the literals, I can formulate 96 different examples. But how many hypotheses can I formulate? What do I have to do to calculate that? What do you think?
Is it 16?
16? No.
I was going to say 64.
No. Why would you think it's less?
All the probabilities. I'm just multiplying.
Yeah, there are no probabilities. There's no probabilities here. Yeah, go ahead.
I'd say it has to be more than 96.
Yes?
Because we have all the possible literals, which were 96, but now we also have the option to put a wildcard and contradiction in each field.
Yes. So if we go here back again, we can do the math again, more or less, or at least do the formula. What would be the math?
Yeah, you would just have to add to each set, like on the left
Yeah.
column, you'd have to add the wildcard
Yes.
symbol and the
Yes.
contradiction symbol
As to each other, yeah.
and then you have to multiply the
Yes.
amount again.
5 times 4 times 4 times 4 times 4 times 4. I'm not that good with math in my head. It's something around 5,000. Yeah. However, as you already rightfully observed, the most specific hypothesis is among them now, but there are many other hypotheses which contain the contradiction, which are also rejecting everything. So we could just collapse them all, right? And that makes the number a little bit smaller, like only 900 or something. It's a different math. You can look it up in the book of Mitchell. It's all written there. All right. So the hypothesis space, this one here we were, is quite large. We have around 1,000 hypotheses to look for. So which one is it that we want to find? One of these is supposed to define that subset X of the feature space that is to be our concept. So our concept is a subset of the feature vectors, and one of these hypotheses, we want to find that hypothesis which defines it. And now we can decide we want to want the most specific one or the most general one that includes it, but there could be more than one. All right. This, what we now saw here as being just informally defined, we can also formally define the more general relation. We have a multiset of feature vectors and 2 hypotheses, or 2 model functions, y1 and y2. It's the same, so it's model function, hypotheses, and the parameters. It's all equivalent here. Y, theta, vector, and hypotheses, h, are all the same. It's just different ways of talking about this, synonyms, as it were. Right? one being more general, more generic than the other. All right, so we have now two hypotheses or two model functions, instantiations of model functions, y1 and y2, and we have our feature domain. Then y1 is called more general than y2, which we denote as greater than or equals g for general, if and only if for all x in x, so for all feature vectors in our multiset of feature vectors, if y2 is 1, this implies that also y1 is 1. We use the implication here as opposed to the equivalence. So the difference here is very crucial, and I will depart now again on the meta discussion of logics. Do you know the difference between implication and equivalence? Good. Can you explain it? Yeah.
I would maybe do it at the example.
Yes.
On the screen right now. So
This one, go use this. This is good. This is good.
yes,
Yeah.
so y2 equals 1 implies y1 equals 1. So this just means that we only, okay, so if y2 equals 1,
Mm-hmm.
then that means y1 has to also equal
Yeah.
1.
Yeah.
But if y2 equals 0,
Yeah.
we don't even have to look at the result of y1.
Why?
Because it doesn't matter.
It doesn't matter. Yes. So you explained in terms a little bit the difference between necessary and sufficient, right? So if y1 being 1 is necessary for y2 being 1, and y2 being 1 is sufficient for y1 being 1. y1 can be 1 without y2 being 1. That's possible. So what's now the difference between this implication and this constraint? Why do I say this here? Why don't I just say implies?
Because it has different possibilities. In imply, it has like, it can be, it doesn't
Yes.
have to be.
Exactly.
Yeah.
Yes. There's a difference that I want to bring your attention to, because here I'm defining something to be the case. So I want it to be the case, and I want it to be only the case if it's actually the case. So in German I place a Forderung. This is what I want more general to mean. I define the semantics. Here it's just a feature of these two functions that somehow has to happen. If that feature, or if that characteristic, or if that relation between the two functions is actually there, then I can say it's more general. Otherwise I can't. And if I say it's more general, then it has to have this characteristic. Otherwise I can't say it again, or I'm making a mistake. So this is the difference between this if and only if and implies. We can also make this definition more strict and say something is more strictly general than the other if we say it's there is no situation where it's the other way around. So this is denoted then as just the greater sign. And in the illustration, we have already discussed that this is the case for H4. H4 is more general than H1 and H2, but neither H1 is more general than H2 or the other way around. All right. Again, lots of this is explained here again. It's not unimportant. It's always good to recapitulate this because it's easy to forget or easy to mix up. Because now we are coming to something that is, again, on a meta level and an important feature of learning, the inductive learning hypothesis. You should read up this in the Mitchell book, which you find online. Any hypothesis found to approximate the target function well over a sufficiently large set of training examples will also approximate the target function well over the unobserved examples. So, if we have this modeling of our hypothesis space and choose a hypothesis, and that find this hypothesis to approximate the target function well over the training examples, we just assume that it will also approximate the target function, the concept, over unseen examples. Remember, we are not enumerating all possible days that could happen, but just a small set of examples, 4 to be exact. We want to learn something from that. Given the discussion that we just had on the previous slides, what is this? Is this logical equivalence or is this an implication?
I think it's implication.
Yes. Can make it more explicit. So, if our model function approximates the training examples, approximating the training examples implies approximating unobserved examples. That is what we do with machine learning all the time. If we choose our training examples well, then this will actually happen. But it could also go heavily amiss. We could also fail. So now we want to look at an actual algorithm that solves this, or that learns the parameters of this kind of model function. We look at find S, find the specific hypothesis algorithm. Input are the training examples that we have, like the 4 that we saw at the beginning, and the output is a parameter vector of all the parameters and that formulate our hypotheses, including the question mark and the perpendicular. So all we want to do is use this algorithm. We use this algorithm to search this space. And we start at a specific place, namely the maximally specific hypothesis. Which one is it again? How does it look, the maximally specific hypothesis? Yeah?
Just contradictions?
Yes, just the contradictions. This one here. Yeah, very good. Go back. Why? All right. So this is our starting point. So we start with the maximally specific hypotheses, and now we go through all the examples in order as they come, and we look only at the positive examples. We ignore if there's a negative one, we just skip it, and we then evaluate the model function as we saw before, just checking its parameter against the feature value, checking whether this binary operator gives us true or false, and whether then the entire function evaluates to true or false, the entire logical formula. And if it evaluates to false, then we minimally generalize the parameter vector for the model function so that it still accepts the positive example. And we continue to do so until all examples are seen, until all positive examples have been seen. Like before, we have the learning step, which is model function evaluation, checking for consistency with the truth, and then calculating a parameter vector update as the least more general hypothesis. So how does this work? We start with the most specific hypothesis, H0, which is given here. And then we look at the first example, and the algorithm sees that it is a positive example, here marked as a plus, and the minimal generalization that would accept this example just puts the example itself as the hypothesis. So the hypothesis is now that my friend enjoys surfing only on days like this. Second example is also a positive example, and we want to now increase the set to include both examples. That means we need to generalize our hypotheses to see that, to include that example as well. And since we have a contradiction here, not a contradiction, but a discrepancy in the examples, in the actual literal, we see that we need to make the minimal operation to make the hypothesis that we are currently having more general is to replace the third entry with a question mark, so that we can accept both normal and high humidity. Yeah.
If there was a third option, would that make it a question mark or not? Like
So if another one differed,
if there were like low, normal, and high for the.
yes, we would not. Yes, you're right. Correct. We don't have other ways of formulating that. Huh? Given the construction of our feature space and our model function, this is the only way to minimally generalize the hypothesis. But you're making a good observation. What does this imply that if there was for example, in the first variable, we have 3 options. If that were different, we would have a question mark here now. What does that imply?
So as long as there's 2 different options,
Yeah.
It would make a wildcard.
Yeah, exactly. But what does follow from that? So you're hinting at a possible problem.
If there was a third option which that doesn't apply, then it would make a problem.
Which has a negative.
If there was a negative.
Exactly. Precisely.
outcome.
Yeah, this was your answer as well, I guess. Yeah. Yeah.
You said that this implies that, for example, the weather either
Mhm.
only gives only one specific weather exists
Yes.
where my friend wants to go surfing, or it doesn't matter what weather it is.
Yeah. Or it doesn't matter, or the variable doesn't matter.
Mm.
Yeah, exactly. That's true. That is the actual correct interpretation in the real world, but it also means that we are now generalizing to a place where we then might already include negative examples without knowing it, because we haven't seen them. So, third example is a negative one, and our algorithm ignores negative examples. So, we skip it. Hypothesis stays the same. And now, the fourth example is again a positive one. We have again a change, I think, here and here. So we have to introduce 2 new minimal generalizations. So we skip one of the levels here in our directed acyclic graph, in our partial order of hypotheses, and land on this hypothesis. All right? And now we went through all the examples, and this is our hypothesis. This is the result. This is the output of our algorithm. This determines whether my friend enjoys surfing or not. Maybe, maybe not. So, did we learn the only concept, or are there others? What do you think? Mm-hmm.
I'd say there are other concepts.
Yes.
Because, I mean, in our final hypothesis, we say that the wind must be strong,
Mm-hmm.
but we have not looked at any object where the wind wasn't strong,
Cool.
so we can't actually say if this is the case.
This is our example. These are our examples. We don't have other examples. We can only learn from the examples. So, yes, there may be other hypotheses, but you cannot argue about things that we have not seen. So, where are these other examples? The other hypotheses, sorry. Can you find them here on the graphic somewhere?
We can make other concepts from the the other question mark, like if
Yes.
we put, for example, if we keep the worm and the other, but keep the other two question
Yeah.
marks.
We can always make H4 more general, and that would include all positive examples. Very likely. So that is always possible. Does not, we have to make sure that the negative example, but it is, we only look for the positive examples. So these hypotheses here, since we never learn from negativity, we only look at positivity. All of the more general ones still accept our positive examples, and they could be hypotheses that are actually true. We don't check that, but they could be. So why should we then just look for the most specific hypothesis?
Because it's easier to generalize from there.
No, we could change the algorithm and start with the most general hypothesis and make it more specific as it goes. Also possible. Just reject all the negative examples instead of the positive ones. So you could rewrite this algorithm, find most general hypothesis. You could do that, no problem. Why should we go for the maximally specific then? So if you don't find a reason in the specific example here, do you find a reason in machine learning in general? Yeah.
Okay, I just wanted to answer regarding why we don't build the algorithm the other way around.
Yeah.
I think the maximally specific hypothesis would be that the object has to look like the one we're currently
Yes.
looking at.
Yeah, that's true. Yeah. We could, as I said, we could just reject all negative examples, build an algorithm that just gives us the hypothesis that says all the negative examples that we have there are rejected, and then it still would be consistent with all the positive ones as well. So we would have learned from the data something, but look back at the real world. I want to give my friend a good classifier, whether they enjoy surfing when they look at their temperature or whatever, like their weather thing. Yeah.
So it really depends on the question that you ask, or the purpose of why you're doing it, or
They want to decide whether they should prepare go surfing. Takes an hour.
so if it would be the other way around, if we
Yes.
would ask when he wouldn't like to go,
Yes.
we would.
Yeah, but we could ask that, but then the decision would be all the same. They would go surfing or no.
Yeah.
What would be the difference in reality?
If we start from more general, then can it be that we might reach false outcomes?
This is always the risk of machine learning, of course, but this is to be discussed a little bit later, that we might reach false outcomes. Yes, machine learning is inductive in nature. We just learn from a few examples a rule about reality. I give you the answer. With the most specific hypotheses, my friend would go surfing on less days than with the most general hypothesis. That's all. And the question is, where is the true hypothesis? Do we have the true hypothesis that really captures all the days? This cannot be answered here, but this is a discussion that we're having, and this is therefore important to learn something. This is something that we are being conservative about our hypotheses. I don't want my friend to waste time preparing for an hour, driving to the beach and getting ready just to notice, it's not funny, I go home again. So I just am conservative with my classifier, just give him the days where he will definitely enjoy, given the examples that he gave me. The most specific hypothesis. But I could go the other way around, just let him go anyway, whenever he might enjoy.
always used like this in machine learning, or does it change? Like, do they always use the maximum specific hypothesis, or does it depend on the
It depends.
type of learning?
It depends on the real world task that you are wanting to solve. What would be the most safest option? Is it the beta classifier that saves my friend time preparing and being disappointed when they see my classifier was wrong? Or is it the beta classifier that just that just maximizes the times they would enjoy surfing, even on days where our most specific classifier would have kept them home? I don't know. This is something to be discussed. I don't know. Yeah? We could transfer this to medical testing. On medical tests, you usually want classifiers that don't tell everyone has cancer. But it depends. If you are doing screening and have a very cheap test, then it's okay if the test says more often yes than no. You can always do a more expensive test later to figure out what is what, which is what happens all the time in medicine. So it's really to be discussed what we want. Inconsistencies in the training example remain undetected by this algorithm. It just generates the most specific hypotheses somehow. It doesn't check whether there's a negative example which contradicts the positive one at all, because we ignore negative examples. And we also don't learn whether our hypothesis structure is appropriate for this learning task. This has to do with the simplicity of our hypotheses. We just have conjunctions, like logical formulas with and, nothing more. We could formulate different hypotheses. And this is what comes next with the version space. We might still have time to get there. So the version space we define as the subset of all hypotheses, of the hypothesis space, which, given an example set D, is comprised of all the functions in the hypothesis space which are consistent with the examples. So HD is all the functions so that the function is part of the hypothesis space, and for all examples that functions is consistent. This is how it looks, starting with the most specific hypothesis. This is the one that find S found us, and being the subset of the directed acyclic graph of the hypothesis space that is delineated then by the most generic hypotheses. So it could be in parallel on the same level, but all in between, all minimal specializations or minimal generalizations in between here, and there could be more levels in between these two sets, they are part of the version space. And this is basically the boundary of the version space toward specificity or toward generality. So the boundary sets that I just showed here, they are also defined here now in much the same way. I will skip this. And what we want to get at now is to get at a version space representation. So we still have our multi-set of feature vectors, we do have our two classes, and a hypothesis space of Boolean functions with the domain X. And we have given a data set of examples. Then, based on the more general relation, each member of the version space lies between the two sets HG and HS. So this is just a theorem we can put forth based on our definitions from before of more general than and the version space here. So all we need to do is prove that theorem, but I will not prove it to you. This can be proven, but I will not show it to you. It's not necessary now. This leads us to a new algorithm, an alternative to the find S algorithm. It finds us both HG and HS, the sets of the most general and most specific hypothesis, which creates the version space. Input is again the training examples, and the algorithm is called candidate elimination. We start with the most general hypothesis in HG and the most specific hypothesis in HS, And then for all examples, we loop through all examples. This is a bit shorthand here to make it fit on the slide. We then look first at if the example is positive, then remove from HG any hypothesis that is not consistent with G. And for each hypothesis in YS, which is not consistent with X, we remove it from HS and add the minimal generalizations, all minimal generalizations to S that still fit. So that Y is consistent with X and some member of HG is still more general than Y. So we don't overrun the other set, so that we don't overrun the lower boundary or the upper boundary. And then we remove from HS any hypothesis that is less specific than another hypothesis in HS. And the same happens in return for HS. If we have a negative example, for HD. If we have a negative example, we remove from HS the hypothesis that is not any hypothesis not consistent with X. For each hypothesis YG that is not consistent, we remove it from HG and we add all minimal specializations to that set, which are consistent with X and which are not more general than, more specific than some member of HS. All right. So here's an example for the examples that we already saw. And we start with the first examples again, which gives us a positive example, and the minimal generalization is here. Nothing happens here because there's no hypotheses that would not accept this example. All these hypotheses here are supposed to accept the example. So this does and this does. Next example, just like find S, we generalize it a little bit more. Next example is a negative example, and now for the first time we learn from negative examples. We find that this accepts the negative example, so we need to minimally specialize it in order for it to not accept this example, while any hypotheses in here should also be consistent with the positive example, so be more general than this hypothesis. This is why we do not have other hypotheses here that we could also formulate based on this negative example. They are immediately removed again. And then with the last, we get to this set. So this is, you can look up in the algorithm and see how it works. So this is what we saw before. After 4 steps, this is our version space again. All of these hypotheses could be capturing the concept of enjoy surfing. Any one of them could be the true hypothesis. We don't know which, but any one of them could be. So, what about selecting examples? And I will go through the first 3 now directly. The other you can read up in the Mitchell book. So, the order of selecting examples plays a role in how fast we learn. How fast we learn the version space. The question now is, if I'm being given that example, or no, the question is, which example should I choose next to learn from? And this example is a very good choice. Warum or why? Sorry, I'm overrunning a little bit. What do you think? Check the example against all of these hypotheses, whether they accept it or not. What's with this hypothesis? Is the example accepted by this one?
It doesn't.
Sunny, warm, fits, question mark, fits, strong, light. No, it rejects. What about this one?
It doesn't.
Okay, this one? This one?
Doesn't.
This one?
It does.
This one?
Does.
Okay. Did anyone keep count?
Yeah, so you have 3 hypotheses
Yes.
remain.
Yeah, exactly. So if we now use the candidate elimination algorithm on this example, we would lose at least half the version space, which is good. We are learning fast, zeroing in on the true hypothesis. So we should choose that hypothesis next, that example next to learn from, which is which helps us learn fastest. So maximally learn, and that in the case of this algorithm means which halves the number of hypotheses we still have to consider, or close to halves. Yeah. And if we always find the next example that halves the version phase, we are learning in logarithmic speed, which is nice. So another way we could look at the version space is using all these hypotheses as an ensemble. Ensemble decisions work like this. We just evaluate every new example, not to learn from it, but just to decide about it, by evaluating all different hypotheses against each example and counting how many accepted and how many rejected. And for the 5th example here in the table, we see that all 6 hypotheses accepted. Here, all 6 rejected. Gives us strong confidence that this is a day my friend would enjoy surfing, and this is a day where they wouldn't. This example is tight. If we were to ask my friend, again, this is the example that we saw on the previous slide, we could learn most about our true hypothesis and where it is in our hypothesis space. And here, it's not equally tight, but a little bit toward not enjoying. So one way of dealing with this uncertainty is to say that in this case we can go with the majority vote, assuming that the true hypothesis is somewhere here, and that that each hypothesis is equally likely. Then this might be a probabilistic choice. But if we don't assume all hypotheses to be equally likely, then we cannot make this decision, and we might just say, I don't know. So this leads us to an important concept in machine learning, which is inductive bias. Here we have 2 additional training examples which lead us to the situation which you hinted at before already, that we have 3 variables, but from 2 examples we already learn a question mark because of the contradiction here. And if then now an example comes where everything, all else being equal, the 3rd option says no, that means we cannot learn at all because our HS becomes empty. None of the hypotheses that remain are still specific and consistent with our positive examples. That is, none of the hypotheses in our hypothesis space are sufficient to explain the situation. This is what you hinted at. We just have the question mark, and once it's there, it accepts everything which is in the domain of this sky variable. And since we have never seen what happens when all 3 values are set, then we have a problem. So, the discussion about inductive bias is what assumptions went into constructing our model function, our hypothesis space. And since we are running a little bit out of time, I will give you the answer. We have made a very simplifying assumption by just accepting conjunctive hypotheses. We can relax that, no problem. Just accept all kinds of logical formulas. Logics, in that sense, if we accept disjunctions as well as the negative, the negation into our logical formulas, we can define any subset of our feature set that we want. However, what happens to the size of the hypothesis space if we accept all kinds of logical formulas?
Then it would assume the
No, what is about the size of the hypothesis space? So here we said we have about 1,000 hypotheses actually. How many are there now?
Way more.
Yes, exponentially more, 10 to the 28. You can read it up in the Mitchell book. It's a lot. So this is part of the idea of inductive bias, that when you want to learn something, you need to make simplifying assumptions. You need to bias your learner. Not bias in a bad sense, but you need to make an assumption about the real world that helps you explain it. And we made a very strong assumption, reducing the hypothesis space to almost 1,000 cases only, or less than 1,000 cases only, saying that all other hypotheses that we could think of in the logical formula world are definitely a no. We don't care about those. This is a strong assumption, and it could lead us to a situation where we cannot learn anything because we made it too simple. However, there is the idea of Occam's razor, and Occam's razor dictates that the simplest solution or the simplest explanation to a phenomenon is the best explanation to a phenomenon. This is how natural science has worked all the time, as long as it is there. And it is also how we want machine learning to work. We want to give us the simplest solution. Because the problem with inductive bias is, and this is now how Mitchell defines this, we define inductive bias as the policy by which the learning algorithm generalizes from observing training examples to classify unseen instances. And what inductive bias is actually is the additional assumptions that logically we have to add to the data in order to then deduce the actual classification instead of making an inductive leap based on the hypothesis. So the assumption here that we made with our conjunctive hypothesis space is that the hypothesis is in there, the true hypothesis. This was our assumption, that we have to add to the data in order to say whether there is an actual true hypothesis or not. Again, in the book it's a little bit more, and we are, as I said, we are running out of time, but this is not an unimportant concept. I invite you to think about this a lot more. Because we will make all kinds of simplifying assumptions all the time in all machine learning. And if we don't, if we allow every possible logical formula and don't have a way of distinguishing between good formulas and bad formulas, what will actually happen in our candidate elimination algorithm is that it will just learn the examples by heart. The most specific hypothesis will just be the set of positive examples, and the most general ones, no, the other way around, the most specific hypothesis will just be the set of negative examples. And that means whenever we get an unseen example that was not part of our examples, we don't know anything to say. We don't know where it is. Because everything between this version space is exactly halved as we allow everything, every subset, every possible subset of the multiset of feature vectors. This is now, you have to take my word for it now, I'm not proving this to you, but it's the case. And since we have the potential of 2 to the x, to the size of x elements that could be in any subset, learning means without a priori assumptions about what we want to learn or how the real world is actually constructed means we cannot learn, as we have no inductive bias. So we need to make simplifying assumptions. We need to say how the world actually works. And this is what machine learning is all about, figuring out what is a right inductive bias. Find S, I'm not asking this of you now, find S as a higher inductive bias than candidate elimination. Since find S makes just the conjunctive and just asks for the most specific hypothesis, not anything else. Candidate elimination gives us more possible hypotheses to choose from. Yeah, and this is it. Thank you. Sorry for overrunning.